Here in Chapter 22, we're going to look at a category of reactions that we refer to as carbonyl condensation reactions. These carbonyl condensation reactions, they're all related to each other, and there's some similarities. There's also some key differences. As we're going through, I'll point out what the different reactions are. The very first reaction that we're going to look at is called the aldol reaction. So let's get started. So the aldol reaction is a reaction where we have an enolate that reacts with another carbonyl to form a new carbon-carbon bond. Now, these can be two of the same molecule or two of different molecules, and we'll talk about that. But the key is that one molecule is going to act as the nucleophile, and that's going to be an enolate, and the other is going to act as the electrophile that is not in the enolate form. So when these react, we're going to form a new carbon-carbon bond, and we can protonate this or go on to do some other reactions with this. It just depends on which variation of the aldol reaction we are doing. So let's take a closer look. So here is an example of the aldol reaction. And this is the simplest possible example of the aldol reaction. It is a reaction between two molecules of acetaldehyde. This happens to be the smallest molecule that you can do an aldol reaction with because it has the two key components. And the two key components are that you need a carbonyl and an alpha hydrogen. And so since this has a carbonyl and an alpha hydrogen, we can do the reaction. And we're going to form a new bond between this carbon, the alpha carbon, and the carbonyl on another molecule of acetaldehyde. And the result is that we will get a beta hydroxy carbonyl compound. Let's look at the mechanism. There's a three-step mechanism, which is pretty simple. The very first step is going to be the deprotonation of our alpha carbon on one of our molecules of our carbonyl compound. So we deprotonate that alpha carbon to give us a resonance stabilized enolate. That enolate will now react with another exact same type of molecule, so acetaldehyde as well, do a nucleophilic attack to give us a tetrahedral intermediate. That tetrahedral, we've seen this tetrahedral intermediate before. That tetrahedral intermediate will then get protonated by water to give us our beta hydroxy aldehyde. And that is how the aldol reaction works. Now, there's some variations to this, and there are some caveats that I'm going to give you, but that is the essence of our reaction. Let's look at some of the features of the aldol reaction. Well, first of all, and this is our mechanism again. First of all, it has a reversible equilibrium, meaning that technically all of these steps are reversible. Now, the most challenging of those is the formation of the carbon-carbon bond, but technically all of these are reversible. We're using hydroxide as a base. Hydroxide, its conjugate acid is water, and so water has a pKa close to 16, it's like 15.7, and our aldehydes typically have a pKa somewhere around 17 or 18. I think this one is about 17. All right, so since the base, or since that what that means is that this reaction is going to favor more. It's going to favor more of not being deprotonated. We're not going to deprotonate all of our alpha carbons. So we don't get 100% of this get converted into the enolate. Well, turns out that's a good thing, because if we deprotonate 100% of it, then there will be no carbonyls. There'll be no carbonyls for this to react with. So we will find that when we carry these out with aldehydes, the reaction does tend to favor the products. And with ketone, it tends to favor the reactants, but there are some tricks we can do to drive the reaction so that it forms products. So the aldol reaction is a nucleophilic addition. We have looked at nucleophilic addition and nucleophilic substitution over the past 5 chapters, and so you have become quite familiar with those. But this is a nucleophilic addition. We've seen it where we have a nucleophile react with an aldehyde or ketone, and it gives us our tetrahedral intermediate, and then we usually protonate it, and we say we're done. With the aldol reaction, same thing. Our nucleophile in this case is an enolate. That enolate will react with our carbonyl, we'll get our tetrahedral intermediate, and then we come along and protonate it. So let's look at another example. This time we're going 1 carbon bigger, and when we go 1 carbon bigger, it's going to be propanal instead of acetaldehyde. So we'll take 2 molecules of our propanal, and those two molecules of propanal, well, one of the molecules is going to get deprotonated to become an enolate, and that becomes our electron-rich nucleophile. That reacts with another molecule of propanal, which is acting as our electrophile, and that gives us our tetrahedral intermediate. Since we do this reaction with water, because it's hydroxide in water, we can protonate that alcohol or protonate the alkoxide to give this beta hydroxy aldehyde. So we want to look at writing out some of these aldol reactions. So let's look at some specific examples. All right, so here I've got an aldehyde, and the way that I want you to kind of think about this is that we need we need 2 molecules of this. One is going to become the beta hydroxy part, and one's going to remain the aldehyde part. So the way I recommend drawing this is that write out this molecule, except instead of putting this as a carbonyl, put it as an OH. All right, and so this is the part of the molecule that was the aldehyde that was acting as an electrophile. Now let's draw the new bond that was formed, the new carbon-carbon bond. And so now this carbon was the alpha carbon on our carbonyl. All right, so we'll go ahead and complete writing out that carbonyl. This alpha carbon also had this benzene ring, so we can draw that here. And that is our aldol product. So that is our aldol product. All right, let's do the same thing with this one. So again, we're going to redraw this, except we're just going to put an OH instead of the carbonyl. We're not going to draw the hydrogen. The hydrogen is implied. All right, and we'll just put that there. I got a tert butyl group there. Now we're going to draw our new bond that was formed between the alpha carbon of 1 and this carbonyl. And we'll go ahead and draw in that carbonyl. All right, and the thing that we have attached to our alpha carbon is a tert butyl group. So we'll go straight down and we have that tert butyl group. And so that is the product of doing an aldol with this particular starting material. All right, now we're going to look at some ketones. And with the ketones, one of the things I find kind of helpful is with a ketone, draw the ketone first. Now, you don't have to do it this way, but if you have a ketone, I like drawing the ketone first. So draw the ketone, all right, and then draw the other part. So we're going to draw, this is our alpha carbon that's there. We're going to draw our new bond that was formed between our alpha carbon and a carbonyl. We know that carbonyl got turned into an OH, and that on that carbonyl we have 2 methyl groups. So we'll go ahead and we'll draw those 2 methyl groups. And so that is the product. So that is our product. All right, we're going to do the same thing with this ketone. So we'll start by drawing the ketone first. All right, now that we have that ketone, we're going to draw the new bond that was formed between our alpha carbon and our carbonyl. We'll have an OH that is there. And then here we've got two carbons, but they're part of a ring. So let's go ahead and draw those two carbons. And now let's finish out that ring. It's not the most beautiful cyclohexane ring, but it'll work. And so that is our product of the condensation between two molecules of cyclohexanone. Now, we want to look at something that we refer to as an aldol condensation. The aldol condensation is where we get the normal aldol reaction occurring, but under the basic conditions, it can go a step further to give us dehydration. And so we could do this with acetaldehyde. And so with molecules like acetaldehyde, we can isolate this beta hydroxyaldehyde. But if we increase the temperature some and continue hitting it with the base, we can get an alpha beta unsaturated carbonyl compound. And so when we do that, that is called aldol condensation. Now, for some compounds, it's very difficult to form the beta hydroxy compound. And in this case, with acetophenone, if we do the aldol reaction, we do form this, but it is not isolated. And the reason for this is that even under moderate conditions and at room temperature, we will typically form the alpha beta unsaturated, which gives us not only conjugation with the carbonyl, but conjugation with this aromatic ring. So we call that the aldol condensation. We want to be able to recognize when the aldol condensation occurs, and we want to be able to do retrosynthesis with it, which we'll talk about here in just a bit. The mechanism of dehydration is a new mechanism, one that you have not seen before, at least not in the sequence that I have taught it. And the mechanism can be drawn like this. In the very first step, the base will deprotonate the carbonyl to form a resonance stabilized enolate. That enolate, we can have it's resonance stabilized, so we got partial negative charge on the carbon, on the oxygen, but we're interested in that partial negative charge on the carbon. And when we have that, we can lose the hydroxide. The hydroxide can be eliminated, and that lone pair of electrons will form a carbon-carbon double bond, or a pi bond, and so that is our elimination. We have a special name for this. The name for this particular type of elimination is called an E1CB. And the reason we call this the E1CB is it is an elimination, so that's where the E comes from. The 1 means unimolecular. It is a first-order reaction. So it is a first-order reaction. And then the CB simply means conjugate base. So this is the E1CB mechanism. If we look at the E1CB and compare it to other mechanisms, like the E1 and the E2 mechanisms that we discussed back in chapters 8 and 9, we'll find that like the E1, it requires 2 steps, where the first step is going to be deprotonation and the second step is going to be the elimination. But with the E1, that first step forms a carbocation, and in the E1CB, it forms an anion. So normally, when we eliminate hydroxide, that's not a very favorable leaving group. Hydroxide is a poor leaving group. But when we form the alpha-beta unsaturated carbonyl compound, that gives us conjugation, and that conjugated double bond does make up, to some extent, for the poor leaving group. All right, so dehydration of our aldol product will drive the aldol reaction to the right. So by dehydrating it, it's difficult to do the reverse of this dehydration, and so as a consequence, we will find that once we form the condensation product, it doesn't tend to go back to reactant. Let's look at number 3 on our assignment. So we'll switch over. And so here we want to see what unsaturated carbonyl compound is formed by dehydration of each beta hydroxy compound. So here, I think it's worthwhile to label what your alpha carbon and your beta carbon are. So our alpha carbon is going to be this carbon here, and our beta carbon will be the one with the OH. So it's pretty easy to identify your beta carbon. It has the OH, and it's 2 carbons away from our carbonyl. That means that we're going to get a carbon-carbon double bond between those. So this will form this alpha-beta unsaturated carbonyl compound. All right, on this one, again, our alpha, so here's our carbonyl, there's our alpha, and our beta is over here. And so we will form a new pi bond between those. So let's go ahead and draw out all of this. All right, so we've got the benzene ring. All right, so there's the other benzene ring. We'll go ahead and draw this carbonyl. So there is our carbonyl, and then we'll have a double bond there. So we'll have that alpha beta unsaturated compound. All right, on this one, again, pretty easy. Our alpha is here, and there is our beta. And so we're going to put a new double bond in between those. And we'll have a double bond there. All right, so we now want to look at some retrosynthetic analysis with the aldol reaction. So identifying in a product where the alpha, identifying in the product where the new carbon-carbon bond was formed. And once you do that, you should be able to do the analysis. So what starting material is needed to prepare this compound? So here's the compound we're interested in making. And so what aldehyde would we need to make it? The thing you want to do is you want to find the alpha and beta carbon. You'll locate the alpha carbon, and the beta carbon, again, is going to have the OH. So we'll locate the alpha and beta carbons, which are right here and here. And then we're going to break the molecule apart between that alpha and beta carbon. The alpha carbon will be where the enolate formed, and that'll give you one molecule of your aldehyde. And the beta carbon is going to be the carbonyl of this one. So you'll see that when we break that apart, this will be where our alpha carbon is, and that was our beta carbon where this carbonyl was. These are the same molecule. We're still looking at doing aldol reactions with the same molecule. So now let's do another retrosynthetic analysis, but on this one, we're going to be looking at an aldol condensation, not just the aldol reaction, but the condensation, where we do the E1CB elimination between our alpha and beta carbon. So there you just need to find that double bond. That double bond are the alpha and beta carbons. So locate your alpha and beta carbons, and then that was the new bond that you formed. And so since that's the new bond that you formed, the beta is going to be a carbonyl. So in this case, it's a ketone, and the alpha is going to be the alpha carbon on the other molecule of the carbonyl. You'll notice here that we've got cyclohexanone as our 2 starting molecules. Let's look at number 25. And again, we're just trying to find where our alpha and beta carbons are, and in doing that, we should be able to do this. So here we have our OH, and here's the carbon adjacent. So this is our alpha carbon, and this is our beta carbon. So since that's our alpha and beta, this was the new bond that we formed. So we'll just kind of cut that apart. And I'll draw this. So 1, 2, 3, 4, 5. So that was our aldehyde. And if we look at the other one, 1, 2, 3, 4, 5, we should have 2 molecules of the same thing. So we can draw that like this. Well, I'm not going to draw it because it's the same molecule, but 1, 2, 3, 4, 5. And so that is the molecule that we had. All right, here is our aldehyde, and there is our hydroxy. So our hydroxy is the beta carbon, and our alpha is right there. So we're going to sort of just cut a line there to indicate that we have cut that. As far as drawing what our aldehyde is, let's go ahead and draw this benzene ring. So there is our benzene ring. There is a carbon that comes down, and then we have an aldehyde. All right, and the other one you'll see is a benzene, and then here is that CH2, and then there is the carbonyl. And so that is the molecule that we use to make this particular one. All right, on this last one, finding the alpha and beta carbons, it's really easy because we have a double bond. So we have an alpha there and the beta there. So the alpha is the one that's directly adjacent to the carbonyl. So again, we're going to just kind of cut that off. And so that means our starting material was a ketone in this case. All right, and so that is the ketone. Normally we'd draw that one going up, but I'm drawing it so it looks like this part. The other part is the carbonyl is here, and then CH2CH3 is this component. So that is the molecule, that's the ketone that gives us this alpha beta unsaturated carbonyl ketone. So now we're going to look at something that we refer to as a crossed aldol reaction. A crossed aldol reaction is simply where we have 2 different starting carbonyl compounds. So we can have 2 different aldehydes, 2 different ketones. We're going to look at 2 different aldehydes. So here we have acetaldehyde and propanal. If we take both of these reagents and just throw them together and set up the conditions for this reaction, we're going to find that both of them have alpha carbon or alpha hydrogens. And so if we deprotonate the acetaldehyde, we will get the enolate for that acetaldehyde. That acetaldehyde enolate can react with another molecule of acetaldehyde and will give us this first compound. If that enolate for our acetaldehyde reacts with propanal, we will get this as our product. All right, when the propanal, we have the possibility of it being the enolate. So we deprotonate the propanal. That enolate can react with a molecule of acetaldehyde and give us this third possible product. And it can also react with another molecule of propanal to give us this fourth possible product. Well, with 4 possible products, that's not a very useful reaction. We generally try to avoid reactions where we know we're going to get 4 different things. And on top of that, these would be a challenge to separate. So because they're very similar, they would be kind of a challenge to separate. So how do we make this useful? Well, it turns out that there's a couple of ways to make cross aldol reactions useful, and I will show you how. So 2 situations. One situation is when only one carbonyl compound has alpha hydrogens. And you can do that with compounds like this. So here we have acetaldehyde and benzaldehyde. The acetaldehyde has alpha hydrogens, but benzaldehyde doesn't because the carbon that's adjacent to the carbonyl is an aromatic ring. It's a sp2 carbon. It doesn't have any alpha hydrogens on it. So we can't deprotonate this one. That means that when we do deprotonate the aldehyde, it will react with our benzaldehyde, and that's the only reaction that we can get. Now, because this one is conjugated, or because we have the aromatic ring here, we're most likely to get this elimination. Again, if you have an aromatic ring next to the carbon that acted as the electrophile, you're probably going to get elimination and get the aldol condensation product. And so you'll get, this is cinnamaldehyde. You'll get both the E and the Z isomer. Cinnamaldehyde is a very pleasant smelling compound that is a component in cinnamon. If you use a ketone, this is acetone. If you use a ketone with this aldehyde, you can also get the same thing because this has an alpha hydrogen. You can get that elimination, and you will get this as your product. So both of these products are possible because there is only one carbonyl compound with an alpha hydrogen. The other possibility is that if you have one of your carbons whose alpha hydrogens are significantly more acidic. We're going to look at that on the next slide, so we'll come back to that. So let's look at number 7 on our in-class assignment. All right, so we can clearly see that this particular molecule has an alpha hydrogen, whereas this one does not. So I'm going to recommend that you draw it out the same way that I mentioned earlier, which is draw this compound, but instead of drawing the carbonyl, draw the OH. So 1, 2, 3, 4, and then we'll put the OH there. And then for this component, I did that wrong. All right. So I did that wrong. Let me fix this. This one that is incorrect. So since this one has the alpha carbon, it's going to be the nucleophile, and it will remain intact. So it will remain intact. So when we draw this, 1, 2, 3, 4, that carbonyl will still be a carbonyl, and then we will get CH2OH. So we'll get this particular product. Now, it is possible that if you do this at higher temperature, you could go on and get the alpha beta unsaturated version of this, and that would give us 1, 2, 3, 4. Double bond there, and we would get this as our alpha beta unsaturated aldehyde. All right, here we've got an aldehyde and a ketone. This aldehyde does not have a alpha hydrogen, so that means that it has to be the electrophile. So it's going to be the one that forms the OH. We're going to draw it like we did earlier. So we'll draw this. All right. Instead of putting the carbonyl, we'll put an OH. And then we will put the other components, the ketone, here. And then that gives us that ketone. Now, because this is because this is a ketone and we've got this benzene ring, this is probably going to just go straight on to give us our elimination product. So let's go ahead and write that elimination product. And we'll get a double bond there. Now we can also get a stereoisomer of this. This is the E isomer. Our larger groups are further away, so we can also get the Z isomer if that is a concern. All right, so now we're going to look at another synthetically useful aldol reaction, and this is where we're going to have one that is significantly more acidic. And so you can use, so that's what this page is the one where it's significantly more acidic. So if we have an aldehyde that does have an alpha hydrogen on it, that's fine. If we pick a compound that is a beta dicarbonyl compound or similar type compound, then it is the hydrogens there are significantly more acidic. Instead of having pKa's at around 17 to 19, we have pKa's more in the 9 to 13 range. All right, here is an example, although this one doesn't have an alpha hydrogen, but here we've chosen a purposely more acidic alpha hydrogen. We can deprotonate that alpha hydrogen, and it does the aldol reaction on this carbonyl. And because this is a benzene ring here, we end up, instead of getting the aldol product, we get the aldol condensation product. So let's look at number 9. Look at number 9 on the in-class assignment. All right, so here we've got a 1,3 dicarbonyl system, or a beta dicarbonyl system. This particular one, because it's a keto ester, it's going to have a pKa somewhere at around 11. If it were a diketone, it'd be a pKa around 9, but this one's at around 11. That means this one will act as the nucleophile, and this will act as our electrophile. So this aldehyde is going to be what gets attacked. So let's look at how we can do this. So I'm going to go ahead and draw this compound again. I'm going to redraw this compound. So it looks like this. All right, and then we've got a nitro that is here. And the reason I'm drawing it like this is so that you can see what happens to it when I've rotated it around. So we're going to draw this as an OH. All right, so that's our carbonyl carbon on this aldehyde. I'll go ahead and put the NO2 here. All right, and now we're going to we have a new bond between this carbon and this carbon. So this is now this carbon. And so we have a methyl there. And we'll have actually I'll make this one the methyl, and we'll call this one the isopropyl. All right, so this is here. This is our alpha carbon, which is there. And then this is our carbonyl, which ended up here. Now, again, because this is an aromatic ring, and we'll get an extended conjugated system, we're probably going to just carry this on and do the elimination. And so when we do that, we're just going to draw the same carbon backbone here. Right, and instead of having a hydroxyl group here at the beta carbon, we're going to have an alpha beta unsaturated carbonyl compound. Oh, and we need the one more thing, which is that nitro group. All right, again, just so it's clear, here, this is our carbonyl that was on the aldehyde here, and that's now our beta carbon, and then this carbon became this carbon there. All right. So let's look at an example of how we can use a crossed aldol reaction to our advantage. So if we've got that crossed aldol reaction, our initial compound is going to lose water to form or in this particular example, it will lose water to form a more conjugated species. So again, because our aldehyde here has a benzene ring on it, when we form this product, it will do an additional, it'll get protonated, it'll do an additional elimination, the E1CB reaction, to give us this particular product. In fact, this one is very similar to the one we just did on number 9 on the in-class assignment. All right, now we mentioned about the beta carbonyl compounds back in the last chapter. We will refer to these beta dicarbonyl compounds as active methylene compounds. And really, all we mean by that is that they have fairly acidic hydrogens, much more acidic than we typically see for alpha hydrogens. Just as an example, these are a few that we looked at, some that we looked at and some we haven't. Let's see, this beta diester has a pKa at around 13. This beta keto ester has a pKa close to, let's see, 11. This one, I don't know the exact value for it, but it's going to be close to 11. And this 1,3-dinitrile, it acts similar to a diketone. It also will have a pKa at around 11. So because that is fairly acidic, it's easy to deprotonate these, and then you can use them as your nucleophiles. All right, so let's look at an example of a transformation with an aldol product. So once you've formed an aldol or the aldol condensation product, there's a whole bunch of different possibilities of reactions you can do with that product. We've got a ketone. In this particular one, we've got a ketone and an alcohol, primary alcohol. And so there's a couple of possibilities, and some that we're not even listing here. But we can take this and do a reduction on it. When we do the reduction, we'll get this 1,3-diol. That may be something that we're interested in doing. We can go ahead and do the aldol condensation, where we form this alpha-beta unsaturated carbonyl compound. That opens up some additional possibilities. Once we have that, we could selectively reduce the carbonyl to form an alcohol, or we could do a nucleophilic addition reaction on the alpha-beta unsaturated with something like a Grignard reagent would give us direct attack at the carbonyl. Go back and look at chapter 17 for reactions like this. We get direct attack at the carbonyl, and we can get 1,4 addition if we use an organocuprate. So Grignard or organolithium will give us this. The organocuprate will give us this. And then finally, we could do catalytic hydrogenation with one equivalent that will selectively reduce the carbon-carbon double bond and leave the carbonyl intact. And if you use two equivalents, you can get the alcohol and get rid of this. So there's a lot of possibilities here. And so we want to look at what happens when we do an aldol reaction, and then like what else can we do to it. So let's look at number 10. And I like number 10. It's kind of a fun problem. All right. So what is the aldol product form when 2 molecules of butanol? I have drawn the molecule butanol here. So 1, 2, 3, 4 carbons in butanol. And we're going to draw it kind of like we did earlier when we were looking at our aldol reaction. So 1, 2, 3, 4. And we're going to make this an OH here. All right. And then this is our new carbon-carbon bond that was formed. And this will be an alpha carbon. So we'll go ahead and do our carbonyl there. So 1, 2, and we need 2 more carbons there because it was another molecule of butanol. So that is our product. You can draw this in different ways, but that is one way to draw it. And with drawn this way, it helps us to get to these particular products fairly easily. All right, so we want to look at how can we make each of these. Well, this first one is pretty straightforward. The reagents that we would use to do this would be simply sodium borohydride, because we're reducing that carbonyl and we're not doing anything to the alcohol. So sodium borohydride, and we could use something like ethanol or methanol, typically methanol, as our solvent. So that would just be all in one step. So that one's pretty easy. All right. For this one, we want to convert. Let's see. We want to convert our OH into a methyl, right? So here this is rotated around, and here we've got the ethyl, which is this up here, and our carbonyl is right there. But we have an OH on this molecule, and here we want it as a methyl. So we want to replace the OH as a methyl. Well, there's not a direct reaction we can do to do that. But if we take the compound and in step 1 we do more base and probably heat, that will help to drive this particular reaction to form our alpha beta unsaturated. All right. And I should have drawn it this way, but it doesn't matter. And now we need to use an organocuprate, the methyl organocuprate, to add to do 1,4 addition, where we add to that alpha beta unsaturated. So we'll do CH3 2 CuLi, and then in our third step we'll add H2O, and that will protonate it, and that will give us this product. All right, well, what about this? Well, here we can do the same thing we did to do the elimination. So we can still make this. So if we do that, we'll get 1 hydroxide and heat, and that will give us this up here. And to turn this aldehyde into a primary alcohol, pretty easy. In a second step, we could use sodium. I'm going to fix that real quick because that looked bad. We'll use sodium borohydride and methanol as our solvent, and that will give us the reduced form of that aldehyde to give us this primary alcohol. All right. So what if we wanted to form this alcohol? So again, we want to form this aldehyde. So step 1, we'll use the hydroxide and heat. And with that hydroxide and heat, that will give us this. And then that, instead of doing conjugate addition, or instead of doing hydroboration, or not hydroboration, reduction with sodium borohydride, we can do a Grignard reagent. Now we could also use a organolithium reagent, but I'm just going to pick CH3MgBr, and that will do a Grignard reaction, a nucleophilic addition to this. It'll give the alcohol, plus we'll have an additional methyl. And of course, we need to work it up with water to get our final product. All right, we're now going to look at a type of reaction that we call a directed Aldol reaction. And this is a way where we can clearly define which carbonyl compound is going to become the nucleophilic enolate and which one's going to be the electrophilic carbon. And the way that we do this is by, instead of picking a base that sort of deprotonates, that just deprotonates partially, we're going to pick a really, really strong base, LDA, the lithium diisopropyl amide, and we'll use that to deprotonate selectively. And because the LDA is strong, and if we do this at cold temperatures, we can get the kinetic enolate that is formed. And then we can add our second carbonyl compound after we've formed this enolate. And again, essentially 100% of this will get converted into our kinetic enolate. and then that can add to the carbonyl. We will get this tetrahedral intermediate, which is an alkoxide, and we work it up with water, and we will get this alcohol. So this will be the aldol product. Now, we could take this on further and do the E1CB reaction, but because of the reaction conditions, we're probably going to leave it in this form unless we have some other situation. So let's look at an example of a directed aldol reaction. This is one that's used in a synthetic procedure. There's this molecule, the periplanone B. I'm not sure I said that right, but it is a pheromone that is produced by the American cockroach. Trigger warning, I'm going to put a picture of a cockroach up on the screen. And so here, to make this, we've got this starting material. We use LDA to deprotonate it. That makes it enolate. That enolate can then react with another molecule that is a carbonyl, so a different carbonyl compound, and we will get this alcohol, and then several steps. It's a lot of steps, and it's not very trivial, but with these additional steps, we could make this epoxide compound, which is a pheromone for this particular gross-looking bug. And it's good to be able to make this and not have to extract it from the roach, because the original structure was determined by taking 75,000 female cockroaches, grinding them up, and they isolated only 200 micrograms of this product. And so any that you could make in a different way would be a useful compound. Now, I don't know if this has any uses other than for cockroaches, but it is an interesting compound. So let's look at number 32, and we'll do some directed aldol reactions. So we'll switch over to our document camera here. We've got acetone, and so we're going to treat the acetone, deprotonate that, and we're going to react that acetone with this aldehyde. So the first thing I'm going to do is I'm going to go ahead and draw the acetone, since we know that. And then we're going to draw to our aldehyde. This is carbon number 1. We have 1, 2, 3, 4. So 1, 2, 3, 4. And then that is the OH that we have formed. All right, so that is going to be the product. When we work this up with water, we'll get it protonated. And again, we don't get the elimination product in this set of conditions. It's always a good idea to double check and make sure that you've got the correct number of carbons. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, there's the ketone, 4, 5, 6, 7. So that tells us that we've got the right structure there. All right, let's look at this particular one. Here we've got an ester instead of a ketone. This is one advantage of doing this, deprotonation with LDA. We can deprotonate that. All right, and when we deprotonate that, we will get this particular aldehyde. And we can either draw the ester first. If we do, we're going to need to turn it around. I'm going to go ahead and do it that way. So ETO. There's our carbonyl. There is our alpha carbon. And then here is the other carbon there. So our alpha carbon is connected to our carbonyl on this. So this, that's the carbonyl. And then there is an OH because we have reacted with that carbonyl. All right, so there's our OH. We got a carbon, oxygen, and then we've got this interesting acetal, a cyclic acetal here, and I'm missing one, and it is here. So just so everybody's clear here, I'm going to label this. So 1 is that one, 2, 3, and we'll stop there because that will tell us what we've got here. So 1, 2, 3, and then there's the acetal, and then this methyl is this methyl here. All right, another way you could do this would be to draw this, and like we did on that very first aldol reaction, is to draw this first. This is the same product, it's just drawn in a different way. All right, so I've got everything there. This is the carbonyl carbon. We're going to draw that as an OH. And then we're going to connect that to this compound. So here is our alpha carbon. There's our carbonyl, our OET, which is the ethoxy group. And then we have one additional carbon here, which is that particular carbon on that. So again, this gives us the same thing where we make this 1, 2, 3 to match it up with this. Whichever one you find easier, just do it that way. I would get used to, one thing I would recommend is I would get used to drawing this in different ways. And that way, if a lot of times on tests, they'll have it drawn one way for this, and then they'll have a product that's drawn like a different direction. And when they do that, it makes it hard to figure out what's going on. If you get that situation, label the carbons, the number, so you can see where, you can map them from the reactants to the products. And then the other thing you can do is learn to rotate the molecules around. All right, for the last section of this particular video, we're going to be looking at intramolecular aldol reactions. So intramolecular. Now, intramolecular means within the same molecule. So it is possible to do these intramolecular if we have a dicarbonyl compound. And so here is an example. This is a hexane 2,5-dione. So at the 2 and the 5 positions, we have the carbonyls. And we can get an enolate that is formed by deprotonating one of the methyls on the end. That will react, we're going to do this one, it will react with the other carbonyl, form the aldol product, and if we do it at a reasonable temperature, we can get the aldol condensation product. I think this one is pretty favorable to form that carbon-carbon double bond. I don't know if you could isolate that particular beta hydroxy compound. I think you form the elimination product. So let's look at what happens here with this mechanism. It's familiar because it's the same mechanism. The only difference is that we've got an intramolecular reaction that's going on. So here we've got that 2,5-dione that we just mentioned. So we deprotonate the methyl on the end with an ethoxy group. That creates an enolate. It is resonance stabilized, but we don't have the resonance structure here. That enolate will react with the other carbonyl, and when it does, we will form our very familiar tetrahedral intermediate that we've seen that gets protonated by the ethanol. And under these conditions, the ethoxide will then deprotonate with an E1CB mechanism to give us this hydroxy group, and then the hydroxy group is lost to finish off the E1CB and give us this particular product. So that is when we have a 1,4-dione, which is where they're at 1 and 4, and then we have methyl on the other side. Ring strain is a factor here. We can't go to really strained rings. So you can form 5-membered rings pretty easily, and you can form 6-membered rings. But if you attempt to form something like this, a 3-membered ring, you're going to be out of luck. So if you take that same compound that we had on the previous page and we deprotonate on the methyl, then we're going to get the mechanism that we saw on that previous page. We'll get this particular structure. If, on the other hand, we attempt to write out the mechanism where we deprotonate here at the 3-carbon and then have the 3-carbon attack the 5-carbon to make a 3-membered ring, that is going to be too strained of a structure to form. And so we will not do that, which means since this is a reversible reaction, you deprotonate here, it'll just go back. And so you will not get the intramolecular reaction. So you do get some of this, but it does not go on to make this product. So what about a 6-membered ring? Well, for a 6-membered ring, instead of a 1,4 dicarbonyl compound, we need a 1,5 dicarbonyl compound. And so here we've got 2,6-hexadione, or heptane, 2,6-dione. So there's 7 carbons total. And again, it's going to be a very similar mechanism where we deprotonate. That carbon will react with this carbonyl, and we will get that elimination or that condensation product. Here is an example. I'm not going to go over the mechanism again because it is it's the exact same mechanism. It's just a 6-membered ring instead of a 5-membered ring. But we're going to look at the synthesis of progesterone. This is an important hormone, and we will find that if we take this particular steroid, we can cleave this carbon-carbon double bond here using ozonolysis followed by some reduction. So there we will get this 1,5 dicarbonyl compound, and with that 1,5 dicarbonyl compound, we can deprotonate this. It can react with this carbonyl. We'll get the elimination product. All right, and we can get progesterone. So pretty cool reaction. Pretty cool reaction. All right, we're going to look at some intramolecular reactions, some intramolecular aldol condensation reactions. So let's go back to this. All right, so I find it very useful to label your carbons. I'm going to start with this one. This aldehyde is going to be where the attack occurs. So we get 1, 2, 3, 4, 5, and 6. All right, so 1, 2, 3, 4, 5, and 6. We are going to there's really a couple of options here. If we deprotonate a carbon 2, which, I mean, that will happen to some extent, but it would have to react with carbon 4. That's going to form a 3-membered ring. That's not going to happen. Likewise, if we deprotonate at carbon 3, we'd have to also form a 3-membered ring. Not going to happen. If we deprotonate at carbon 5, that gives us 1, 2, 3, 4, 5 carbons. So we'll get a 5-membered ring. And 4 will still remain a carbonyl, but 5 will come around and react with that. And so let's go ahead and draw this particular compound, or this particular, we're going to draw this particular compound, but we're going to write it in a way that helps us to see what our product is going to be. All right, so I'm going to redraw this, and so I'm going to put carbon 4 here. So there's carbon 4. There's carbon 5 and 6. So there's 6, 5, 4, 3, 2, 1. So that is our aldehyde there. All right, and this will help us to draw our product in a pretty clear manner. I'm going to go ahead and label these again. So 1, 2, 3, 4, 5, 6. I really can't emphasize enough. If you're going to do an intramolecular, label the carbons, and then that way you can keep track of everything, and it's going to go so much better. All right, so now that we've labeled all of those, we're going to deprotonate 5. We'll make a new bond between carbons 1 and 5, and then that will do the E1CB mechanism and eliminate. So that will get converted into this. And again, I'm going to label the carbons with numbers. So 1, 2, 3, 4. There's carbon 4, 5, and 6. So from our original compound to this, those are the molecules. All right, let's do that again. Here we're going to use this dialdehyde. So we've got carbon 1, 2, 3, 4, 5, 6, and 7. So 7 carbons total. Let's go ahead and draw this. We're going to draw it as a kind of set it up. So we'll have our carbonyl, hydrogen. So there's 1, 2, 3, 4, 5, 6, 7. All right, again, I'm going to number these and we'll label them. So carbon 1, 2, 3, 4, 5, 6, and 7. Carbon 2 and carbon 7 are going to react. So we're going to deprotonate at carbon 2. It will react with carbon 7. I probably could have done this going back the other way, but anyway, I turned it around. So 1, 2, 3, 4, 5, 6, 7. And so we'll get a reaction and a condensation between those two. So our product is going to be a 6-membered ring. And we'll have a carbon-carbon double bond here between carbons 2 and 7. Between 2 and 7. And carbon 1 will still be intact out here. And so that will give us that particular compound. So again, we're going to label this 1, 2, 3, 4, 5, 6, and 7. All right. I did not put enough room on here, but that's okay. This one, on this one, let's go ahead and label these 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 9 carbons in this. And there's a couple of possibilities here as to which ones we could deprotonate. If we deprotonate 4 or 2, that would give us the same product. But if you see 1, 2, 3, 4, that would give us a 4-membered ring. It's a little too strained. So we're not going to do 4. We're going to do 6. So if we deprotonate 6 or 9, we'll just look at 6. If we deprotonate 6, 6 will come in and react with carbon 1. And when it does, that will give us a 5-membered ring. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. That'll be a 6-membered ring. I just need to learn how to count there. And going the other side, 1, 2, 3, 4, 5, we will have a 5-membered ring as well. So let's draw a 6-membered ring that is fused to a 5-membered ring. So 1, 2, 3, 4, 5, 6, and 1, 2, 3. If you count, you'll see that we do now have 9 carbons. All right, and we made a new bond between carbons 6 and 1. So we're going to call this one 1. So 1, 2, 3, 4, 5, 6. I went the wrong way. All right, let me fix this. All right, sorry for the confusion. So, 6-membered ring. All right, so we'll call this carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. And so, yes, we're making a new bond between 6 and 1, not between 6 and 9. So 6 and 1. So here, we'll make a new bond there. And so carbon 5 is going to keep its carbonyl. And we will have a double bond between carbons 1 and 6. The oxygen that was on carbon 1 got eliminated in the E1CB mechanism. And so that's where that one went. All right, this next one is challenging. This next one is challenging. Again, I'm going to label this. All right, so when I label this, I'm going to kind of arbitrarily do it here. I'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. I did not label this methyl, so there is a methyl on carbon 4, so we'll need to pay attention to that. And I'm going to draw this in 2 different ways. I'm going to draw one where I've got a 6-membered ring and I have a bridge, so like we're looking at it from above. So I'll do this one. Draw this kind of big here. All right, and this is carbon number 3. So label this. So 1, 2, 3, 4. Let's see, 5, 6, 7. All right, and then 8 and 9 are going to bridge here. So that comes up. There's 8, there's 9, and then 9 is connected to 4, and we'll make that a wedge. So that'll be 8 and 9. All right, now that we have that, so we've got these bridge, we need to make sure that we have all the substituents. So we made a new bond between carbon 2 and carbon 7. If we attempt any of the other alpha, like 6 to 3, that gives us a 4-membered ring. 8 to 3 also gives us a 4-membered ring. And so that is not going to work. Really, the only possibility is to deprotonate 2 and bond that with 7, and that gives us a 6-membered ring. So here is the new bond that we formed between 6 and 7. We are not going to do we're not going to be able to do an elimination, the E1CB, because we can't make double bonds going to bridgehead carbon. So we can't make it to going to here. And that just, it doesn't work. So we will not get an alpha beta unsaturated. And then we also have a methyl on carbon 4. So that is one way of drawing this structure. I'm going to draw the other structure where we're looking at it from the side. And so to draw this, all right, I'm going to draw, there's 8 and 9. And then we've got a bond that's coming down here. This is carbon 4. This is the bond between carbon 4 and 5. There's 6. And then 6 is bonded there to 7, 8, 9, and 4. And then here's carbon 3, 2, and 2 is bonded to 7. We have a methyl that is right here. And we have a carbonyl that is there. We have a methyl on carbon 4 and an OH on carbon 7. Again, I am going to label this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. If you are having trouble seeing this and this is the same thing, I encourage you to get some molecular models and build them. And then you will see that these two things are the same thing. All right, I'm going to double check, make sure I haven't left anything off. I have not. All right, so that is the product. And that is also the end of our first video. I went over an hour. Sorry about that. I went over an hour. Our next video will probably be the last half of chapter 22.